Hello friends, in the present video we are going to study about the stability of infinite slopes. Stability of infinite slopes. So instead of by hearting the formula for the infinite slopes, if you understand the derivation, then that will help us to solve some complex problems. Okay, so let's start with the assumptions that are considered in the infinite slopes. So the first assumption is that the soil mass is considered as a homogeneous. That means along the long distance at particular depth, it is mandatory that uniform conditions will exist. So that's why we are assuming that, okay, let the conditions will be same at a particular depth. And in the next assumption, we will assume that the failure will be due to translation. And sliding of the surface which is parallel to the slope. That means if you are considering some infinite slope, okay, so what we have discussed that at some particular depth we have assumed that along the layer, along the slope, we have discussed that the uniform conditions will exist, but in reality it may not happen. So to avoid that complexity, we will assume that soil mass is homogeneous, and we will assume that the failure will be because of the translation. That means if you are assuming that your soil mass is going to fail at a depth h, whatever the soil above the h, above the depth until h, that will simply slide over the slope surface. So by assuming these two assumptions, now we will proceed to the derivations. Okay, so first let us consider an infinite slope. Okay, and let us assume that you are going to study about the stability of this layer. The layer you are going to study about the stability, let us assume that it is at a distance of h from the ground surface. Okay, now let us consider an element which is having a width b. Let us consider I am having an element which is having width along the slope. Let us say from here to here, let us say the width is b. Let us assume it as a small b to avoid the complexity, confusion. So let us denote some points. Let us say this point is a, and this point is b, and this point is c, and this point is d. And also let us assume that the slope is inclined at an angle I with respect to horizontal, right? Now let us assume that gamma is the weight density of soil. Okay, now what about the weight of the soil? Weight of the soil. So here we are representing a element in the 2D, but in reality if you want to find out weight, it should be in a 3-dimensional way. So that's why I am considering unit length. So this one is along the cross section, and we are considering the length of the element is equal to 1, or else simply we call it as the unit length. So how we'll find out the weight of the soil? That will be equal to weight density into volume of the soil. How we'll find out the volume of the soil? That will be find out as gamma into area of the element into length. How much length we are considering here? Unit length. That implies length will be is equal to 1. Now, what about the area of this? If you find out the area of that element, that will become as, if you find out, that will be as B into H into cos I. So this is nothing but the area of the element. So if you substitute in this formula, then that will be equal to gamma into area is nothing but a B H cos I into 1. Let us say weight of the soil I am representing with by W. So how much we are getting? We are getting a magnitude gamma into B into H into cos I. So this is the total weight of the element that we are considered. Now let us represent the weight of the soil. So this is the element we have considered. The slope of the slope will be, soil will be nothing but I, and whatever the points we are denoted here, A, B, C, and also D. How the self weight will act at any point? That will act truly along the vertical direction. So this is the self weight will always act truly along the vertical direction. Sorry, I'm unable to represent exact vertical line. Let me change some color here. So this is the self weight W that will always act truly along the vertical direction. If we know the weight of the soil, from this we can find out what is the stress acting on the plane CD. So let us say the stress because of the weight of the soil represented by using sigma. So we'll find out the sigma. That will be is equal to, what about the force on the plane CD? Nothing but a self weight W divided by, and what about the area of the plane CD? We are considering then unit length. So what about the width from here to here? From here to here, we are considering it as a B. So what about the area per unit length on the plane CD? That will be called it as a B into unit length 1. So that will be equal to how much we are getting? W. Gamma into B into H cos I divided by B. That will be nothing but a stress, vertical stress on the plane CD. So here I am representing with sigma V. That means it is acting in vertical direction. If you simplify this, how much you will get? Gamma into H into cos I. Now, this is the stress that is truly acting along the vertical direction. But we have to find out the stresses that is acting normal to the plane CD, parallel to the plane CD. So let me draw the stress on the plane CD only in an enlarged shape. Let us say this is your plane CD. Unit length I am not representing here. Let us say the inclination is I. And the stress acting on that plane, this is acting truly vertical direction. Let us say it is acting truly vertical direction having a component sigma V. Right? Now we have to resolve these forces along the normal and tangential direction. Let us represent the tangential and normal direction. Let us say this is your normal direction, right? And let us say this is your tangential direction. So if this is slope is I, then here also the same slope will exist with respect to the normal. That is nothing but a I. So if you resolve this into components, how much you will get? What is the component along the normal direction? What is the component along the tangential direction? Let me represent with some other color. Okay. Okay. If you resolve this into components, how it will look like? The same thing, if I resolve it to components, I am representing on the another plane. Let us say this is the plane CD, and this is the normal to the surface, and let us say this is parallel to the surface. So this sigma V, the whatever the vertical stress, I am transforming it to, I am finding the components along the tangential and the normal direction. So what about the normal component? You will get it here. What about the normal component? The angle is making with respect to normal. So what is the normal component? Cos. So that's why here the component will be sigma V cos I. Similarly, what about the component that is parallel to the slope? So the component that is parallel to the slope, that can be written as a opposite side. That can be written as sigma V sine I. Okay, that means on the plane CD, what about the normal stress? Sigma V cos I. That's why I'm representing with sigma N. What is the stress that is parallel to the surface? That's why as it is parallel to the surface, I'm representing with the shear stress. Okay, now, so on the plane CD, what is the normal stress acting on the plane? That means sigma N, that is represented by using sigma V cos I. Sigma V is nothing but how much you are getting from the previous sigma V, gamma H cos I. So if you replace this term here, gamma H cos I into cos I, that implies how much you are getting? Gamma into H cos square I. So this is the normal stress acting on the plane CD, gamma H cos I. Similarly, what about the shear stress acting on the plane CD, that I am representing with tau? That will be find out as sigma V sine I. So if you replace sigma V here, that will be denoted as gamma H cos I into sine I. So then you are getting the shear stress will be equal to gamma H cos I sine I. Right? So this is the normal stress acting on the plane CD, and this is the shear stress acting on the plane CD. Now, how can we find out the stability? Stability is understanding by finding the factor of safety. So already we have seen in the previous slides, what is the factor of safety? That will be is equal to shear strength divided by shear stress. Now, on the plane CD, that means at a depth h from the ground surface, we have found the shear stress. And from the shear strength of the soil chapter, we can find out the shear strength capacity of the soil. So if this magnitude, if this factor of safety, if it is coming greater than 1, then we'll call it as a safe. If this factor of safety, if it is coming less than 1, then we can call it as a, the slope will be unsafe and the soil is going to be failure. Okay, so here we have found out how we can, so in this derivation we found what is the shear stress that is acting at a depth h. How much it will be? Gamma into h into cos I sin I. So if you understand the parameters here, for the particular slope I will be constant, for the particular soil again weight density will also be constant, but what is the variable parameter here? Your h will be variable. That means if you keep on increasing the depth below the ground surface, then your shear stress will increase. So if your shear stress is increasing, then there may be a probability that chances will occur for the failure. So for the factor of safety, we'll compare it with the shear strength, and wherever this shear strength it is coming less than the shear stress, then we'll say that at that point failure will occur. Okay, thank you.